Very useful property of orbits is used by astronomers to find the mass of the object that a small moon is orbiting. So we have here a problem, hypothetical problem, completely made up, but a small moon of an asteroid. Small means its mass is insignificant compared to the mass of the asteroid. It's observed to have an orbit with a radius of 7 times 10 to the third kilometers. The size of an orbit can be found by measuring the angular radius of the orbit and using the distance to the object, and just S equals r theta, the central angle formula, can be used to approximate the radius of the orbit. So that's a measurement, and it's easy to measure the period of the orbit, how long it takes the moon to go around once to the asteroid, and let's suppose that comes out to be 37 hours. We want to calculate the mass of the asteroid. We're going to have a simplifying assumption that the two objects are spheres, and this r value is the distance from the center of the spherical asteroid to the center of the spherical moon. And that distance 7 times 10 to the 6 meters. So that's from center to center. That's what we need for the law of gravity. The period of 37 hours, hours is not a standard metric unit for time, so we convert that into seconds, roughly 1.3 times 10 to the 5th seconds. The primary concept here is that the force of gravity is supplying the centripetal force. So force of gravity equals F sub c. The force of gravity expression is capital G, mass of the asteroid, mass of the moon, divided by the square of the distance from center to center. That equals the centripetal force expression, the mass of the moon. That's what's moving in the circular orbit around the asteroid, and we're assuming circular orbit. We have the square of the velocity in that orbit, and divide by, again, the radius of that orbit for that moon. So we use that. We also take advantage of the fact that the velocity is circumference divided by time, the period. 2 pi r circumference, capital T, the period of the orbit. So we bring that in because we were not given the velocity of the moon going around the asteroid. We were given time information. So we substitute out the velocity symbol. We didn't know that. When we substitute that, it was v squared in the original expression for centripetal acceleration, v squared over r. So we have to square each factor. The 2 becomes 4, pi becomes pi squared, r becomes r squared, t becomes t squared. And we can solve this now, of course, for the mass of the asteroid. Multiply both sides by r, divide both sides by capital G, and there's our expression for the mass of the asteroid. We were given the size of the orbit, 7 times 10 to the 6. That has to be cubed. We were given the period in hours. We converted that to seconds as we need. So we have meters, we have seconds. And try this on your own calculator, but the mass of this asteroid, 1.14 times 10 to the 22nd kilograms. That's a fairly large asteroid. Again, just random numbers that I chose. If you choose different numbers, you get a different result. But mass of this asteroid, hypothetical asteroid, 1.14 times 10 to the 22nd kilograms. Just for comparison, the Earth is about 6 times 10 to the 24th kilograms, if my memory serves me here. So we have something that's considerably less massive than the Earth, and the asteroids certainly are in that category. If I would have come up with more than 10 to the 24th kilograms, I would have looked for a mistake, because there aren't any asteroids that have a mass greater than the mass of the Earth. So there we are. Key concept is the force of gravity, Gmm over r squared, is set equal to the centripetal force expression, mass of the object in the orbit, times v squared divided by r. Another key concept, the velocity is circumference divided by the period, 2 pi r divided by the time. So practice on that on your own and ask questions.